All right, so just a couple of really quick problems here to help us see how we're going to tie in some of that information from equilibrium to electrochemistry. As you take a look at this first question, it's going to ask us to calculate Q, or that reaction quotient, for a galvanic cell based on the following equation at 25 degrees Celsius, where initial concentration of the cadmium ion is 0.010 molar and initial concentration of the lead-2 ion is 0.1 molar. So hopefully you can begin to recognize where this is going to come into play. When we were talking about calculating things like the standard cell voltage, those standard conditions were 1 molar concentration. So now all of a sudden we've got concentrations that are not 1 molar, and so hopefully you can begin to see where we're going to go with this. All right, so let's set up a quick expression here to solve for our reaction quotient. Keep in mind, you're only going to include the aqueous species in your reaction quotient. You're not going to include solids or liquids. We'll talk about gases when we get to equilibrium. So as I take a look at this, it's products over reactants. So products over reactants. The only aqueous product that I have here is the cadmium 2+ ion, and the only aqueous product I have is the lead 2+ ion. My coefficients in the balance equation is just 1, so I don't need to raise those to any exponents. So I'm just going to plug in my values that are provided to me here. For cadmium, I get a concentration provided of 0.010 molar. And for lead, I've got a concentration of 0.100 molar. And so when I bust out my calculator, this one's pretty easy to do. When I bust out my calculator and solve, I get a reaction quotient value of 0.10. No units for the reaction quotient. And that's all I want you to do at this point, is just recognize how to calculate the reaction quotient. We're going to come back in a couple of minutes here and talk about how that applies to some more in-depth electrochemistry. But this is how you calculate reaction quotient. Just products over reactants, boom, 1 and done. Let's move on to question number 2. It gets a little more complex. As we take a look at question number 2 here, we're asked to calculate Q, again, for a voltaic cell that is set up at 25 degrees Celsius with the half cells there. We've got an aluminum half cell and a nickel half cell, and the concentrations of those half cells, the solution part of those half cells, are given to us as 0.0010 molar for the aluminum half cell and 0.5 molar for the nickel half cell. So here's where it gets a little more complex, and you're going to be asked to sort of tie in some of your electrochemistry. As we come up with the overall redox reaction that's occurring here, we're going to take a quick peek at our standard reduction values to see which one is the most positive, to understand which one is going to be the reduction half reaction. In this case, we're going to have reduction occurring here, again, because we have a larger reduction potential. So as we set this up, we're going to keep that reaction as written. And this reduction potential value for that half cell is negative 0.25 volts. We are going to have to flip the second reaction, so we're going to end up with aluminum being oxidized here, or losing electrons to form the 3+ ion. Keep in mind, our reduction potential is going to stay the same magnitude, but we have to change the sign to positive 1.66 volts. Then you want to make sure that you have the same number of electrons gained as you are losing. We are gaining 2 electrons, each nickel ion is, while each aluminum ion is losing 3. Each atom of aluminum is losing 3 electrons. And so to balance this out, we need to multiply this top half reaction by 3. And this bottom half reaction by dose. That way our electrons will sort of drop out, and our overall reaction to express what's going on in this redox reaction is going to be something that looks a little bit like this: 2Al3+, and then the Standard cell potential for this reaction, we're just going to sum these together and we get positive 1.41 volts. Okay, so now to calculate Q, our reaction quotient for this reaction, whoa. Again, it's product, just brackets to emphasize its concentration, over reactants. The reason why we had to do this is because we need to make sure we had a balanced equation here. And so when we solve this, our product concentration, is going to be the aluminum ion squared, concentration of aluminum ion squared. That's the only one we're going to include because that's the only aqueous, this one's solid, that's the only aqueous ion that we have on our product side. Our reactant side, we're going to have the nickel ion raised to the third power. And then we just need to plug in the values that were provided to us in the initial problem for those initial concentrations. So the aluminum ion concentration is 0.0010 molar. So we've got 0.0010 squared. Again, that comes from the coefficient in the balanced chemical equation. And then our nickel ion concentration is 0.50 molar. It's going to be cubed. When we solve this, we get 8.0 times 10 to the negative 6 as the numerical value for our reaction quotient. And again, we'll talk a little bit more about what that means in relationship to equilibrium for this reaction, the equilibrium constant for this reaction in a couple minutes.